Welcome to this 70 seminar series at the FM Kirby Research Center at the Johns Hopkins and the Kennedy Krieger Institute. So this month, we're very excited to have Dr. Simon Robinson, and he is currently associate professor in Medical University of Vienna. So as he told me, he was originally from UK, and then he spent most of his working life in Vienna, Austria. And recently, he also spent some time in University of Queensland as Australia. And I have to say, as a non-English native English speaker, sometimes I cannot differentiate Austria and Australia. So if I give wrong information, I apologize, and Simon, you can correct me later. But I think in terms of his work, most people here are very familiar. Dr. Robinson has been a leader in the QSM SWI field, especially on high field, MRI. And he's been doing lots of seminal work, especially in functional MRI, fat water imaging, and other areas. So this is also the topic for today, susceptibility imaging at ultra high field. We got lots of interest, from both our, local Johns Hopkins community as well as our online audience from the high field, community from all over the world. So with that, I'm going to hand over to Dr. Robinson, and we very much look forward to your talk. Thank you.
Thanks very much, and so thanks for the invite to join you here. I know it's taken a while for it to work out because I had to put it off once and you had to put it off once, and that spanned then a whole year. So you've obviously got a program that is full of speakers and interest. So I think if you didn't read the abstract for this talk, which of course I'll forgive you for, then you may not know what to expect too much by susceptibility imaging, because susceptibility imaging isn't really the topic of isn't really the title of an MR method. You'll probably know susceptibility imaging from susceptibility-weighted imaging or quantitative susceptibility mapping. But I'm trying to use it here as an overarching topic or title to subsume some contributions both from fMRI and susceptibility-weighted imaging and QSM. And ostensibly, these seem like very different subjects and very different methods. And I'm going to try and pull out some commonalities and some regions of overlap and mutual benefit. So in fMRI, obviously, we're looking at neuronal activation, mostly with 2D EPI, with quite low spatial resolution and high temporal resolution, whereas in SWI and QSM, we'll be looking at veins and iron mostly in SWI, all sources of susceptibility in QSM, generally with a 3D high resolution gradient echo acquisition. So high spatial resolution, low temporal resolution, usually only one time point. So lots of differences there. But of course, we're looking at the dynamic bold effect in fMRI, which is obviously related primarily to the concentration of deoxygenated hemoglobin. And in SWI, we're looking at the static bold effect. So we're looking at the spatial variations that arise in the signal that arise from the concentration of deoxygenated hemoglobin. And in QSM, we're looking at susceptibility and actually all sources of susceptibility, so not just deoxygenated hemoglobin, but also other sources of iron, also myelin and calcium and anything with susceptibility variations. So some sorts of commonality there. And in fMRI, we're obviously looking at magnitude contrast primarily. We're looking at the influence of susceptibility on B0, on regional changes in B0, which then affect T2 star. And in SWI and QSM, we're looking primarily at the phase of the signal and the influence of susceptibility more directly on the magnetic field as reflected in the phase. Both of these areas, or both these topics, methods, benefit from ultra-high field. Both of them use T2 star weighted gradient echo acquisitions. And these extremes that they represent at the moment of the spatial of edges of the spatial temporal resolution scale are really starting to gradually disappear as we move to higher and higher resolution fMRI and to faster acquisitions of SWI and QSM data. So what I'm hoping to do in this talk is to begin with begin looking at these static methods of SWI and QSM, and some methods that we've developed to improve SWI at ultra-high field, coil combination, phase unwrapping, and a multi-echo SWI that we've developed. And then also ending that topic then with some faster acquisition with 3D EPI. And then try and look at how those methods can be applied to fMRI and to get more information out of the phase of fMRI for physiological noise correction, dynamic distortion correction, and then ultimately to derive QSM directly from the fMRI data, where others were also looking at functional QSM from fMRI. And then we'll look generally at how these fields may at some point fuse, and we'll be getting all the information from possibly one sequence. Okay, so let's begin with an overview of SWI and QSM, and this has to start really by recognizing that the phased array coils that we're scanning with consist of a number of elements, a number of overlapping surface coils, each of which delivers a different image. So if we look at 8 channels here and the images from 8 channels, we can see the magnitudes in the background here, and how the variation in the signal magnitude reflects the distance of the object from the surface coils. And we can see here that these phase images are all quite different, and they're different for reasons that we'll look at later, but basically they have to be processed in some kind of way in order to be able to match them and then to generate a combined phase image. Combination of the magnitudes is very simple, so we've got to combine magnitude and phase image as one of the first steps. We then need to remove this artifact you can see here, which we call phase wraps. More about that later. And then in SWI, we are interested primarily in the high spatial frequency changes in this unwrapped phase. So we'll high pass filter the phase, we'll then invert it so that the sign is inverted basically, and then generate a mask out of this. So we're only looking at the effects of the positive phase values, and we'll turn those into a mask, which really reflects veins, which we multiply a number of times by the magnitude to generate our SWI. We could then also develop, also calculate a minimum intensity projection over a few slices. In QSM, we start also primarily with this unwrapped phase image here. We might use the magnitude mostly just to generate a mask. And then there are 2 basic and further tasks in QSM. First of all, we have to distinguish between the external fields. Those are the sources of susceptibility which come from outside of our field of view. And these account for most of the changes in the field. They're basically the interfaces between bone and air and tissue and air, the large susceptibility differences. And by removing those background fields, we end up with the internal fields that are generated by the tissue. And then we what's called invert those. That's remove the influence of the dipole distribution that surrounds these susceptibility sources. So we can get back to our quantitative susceptibility map. So quite a few processing stages there. And we'll see that ultra-high field, a lot of these need to be reconsidered. And I'm going to be looking here primarily at these steps early in the pipeline, but then following them all the way through to SWI and seeing that they're also going to be needed for QSM. So why is this of such interest at ultra-high field? Well, SWI really is quite literally a poster child for ultra-high field. You'll see SWIs on all of the vendors' posters at conferences with this kind of comparison. This one is one I did myself, so I can say it's quite fairly matched for acquisition time. But you can just see a lot more, visualize a lot more vessels at 7T than at 3T. Due to the you've got shorter T2 stars, so we need shorter echo trains, higher signal to noise, so it can move to resolution in the same imaging time. So this looks great, but if we dig down a little deeper in the brain, we can see that we get this kind of SWI using the vendors SWI, and this was something that we set to work on when we got our 7T. So in parallel to the clinical studies, we tried to sort out some of these problems because we've got signal loss around here, we've got an inhomogeneous image, we've got these residual wraps and phase artifacts, and we need to get rid of all of those. So you can see those problems there. So, and these all arise from the fact that basically SWI was developed by Jürgen Reichenbach and Mark CAIPI for 1.5T, and there they used complex valued high pass filtering, which works very well at 1.5T, and that subsumed the functions or the steps that I've looked at before of coil combination, phase unwrapping, and high pass filtering. And though that method doesn't work well at ultra high field because of inhomogeneities, both in the static magnetic field and in B1. So also that high pass filtering makes the phase data unusable for QSM. So we need to reconsider it also for that purpose. Okay, so let's begin with this problem of combining phase images from multi-channel coils. And as I said, these phase images there look very different from if we pick out 8 of these channels. And if the expression for the evolution of the phase over time from a particular, so this is the phase from a particular coil C as a function of time, is equal to, let's look at this delta B0, the local difference from B0 times the echo time times the gyromagnetic ratio. So it's this delta B0, which is usually of interest to us. But we also have this second factor here of the receiver phase offset, also sometimes known as the initial phase, because it's the starting value from the phase. And if this was a perfectly shimmed voxel, the phase would proceed then flatly from here, but in fact, the gradient here reflects the regional variation, the regional deviation, sorry, from the static magnetic field. And we've got this factor of the initial phase to contend with. So where does this come from? Well, it's got many contributions actually, and some of them are unique to each coil, like delays in the RF chain, it's cable lengths and things like that. Any imposed phase shifts we might have, say from B1 shimming. But most importantly, we've got the coil sensitivity, which is not a scalar, it varies in 3D. And that's what gives rise to the majority of these phase variations we can see there. We've also got some contributions which are the same for all oil coils, like the transmit phase. There can be a gradient in the phase in the readout direction that might come from any mistiming between the acquisition and the gradients, and also any eddy current effects. And also if the gradient evolution is not linear, then any non-linear terms can also end up being attributed to assign to this phase offset here. So we can calculate this phase offset here if we've got multiple echoes. So if we just write down the same equation again, but for the 2 echo times and rearrange to solve for the phase offset, we can see that that's just related to the unwrapped phase at time first phase and the second phase with scaled by the echo times. So we can just rearrange that slightly to take out the first phase, and then we've got the scaling factor and the difference between the phases at these 2 echo times. And that's the same for all coils here. And we've got the scaling factor here. So what we can do is just calculate the complex difference between the first and second echo times over all channels. So we take what's called the emission inner product, the angle of the complex phase difference. Then if we unwrap and scale that and subtract it from the first echo time, we get to these phase offsets. We can then remove them from the phase at each echo time, and then we should have matched phases. What we realized here is that this really is the problematic step, the unwrapping of this phase difference, because that's not necessarily a very robust process, and it can be quite time consuming, and it makes it a bit difficult to do that on the image reconstructor. So we realized that if this factor S here is an integer, then wraps in this term here then are actually irrelevant, and we can make S an integer just by making the second echo time twice the first, which is usually quite an easy condition to multi-echo gradient So in that case, we don't need to unwrap here. We just subtract this, this complex difference from the first echo time to get the phase offsets. And we can then smooth them because they don't contain any interesting fine frequency information. So that just removes some noise. And then we subtract them from the first echo time. And you can see we've got very nicely matched images from all the coils here. We can calculate then, sum them over channels and calculate the angle of that. And this is the method that we call Aspire, which we've implemented on the imagery constructor from VB, also VE. So some people use this at 3T as well for comparison studies. And we're going to bring this out for XA soon. So if that's a bit Siemens related, but this is now in use at 49 ultra-high field sites. And that really forms the kind of backbone of our other developments. So if we move to the second step now of this process, the problem of phase unwrapping, then this arises really because the phase that we measure is limited to a range of 0 to 2 pi, or it's at least limited to a range of 2 pi, whether you scale it between 0 and 2 pi or minus pi and plus pi. So that once we get through 2 pi here, it's equivalent to getting through a full revolution, then we measure the remainder. So what we measure in phase imaging is the remainder after a mod 2 pi operation. So our challenge in phase imaging, in removing the wraps, is to identify where these wraps have occurred, either moving from voxel to voxel or from defining regions and moving from region to region. And then adding, for instance, in this case, then 2 pi to the voxels on this side of this phase wrap here to remove that. That gives us our unwrapped phase image that then reflects things like the static magnetic field. So we wanted to do that both for high resolution gradient echo data, but also for EPI data. In particular for EPI, it has to be very fast and robust. We looked at existing methods and we found that Prelude, which is probably the most commonly used method by the FIMRIB FSL group, it's robust. It's a region growing method, but it requires a mask, which itself can be a little problematic in QSM. And it can take hours or days for highly wrapped data. There's a faster method called Best Path, which is a voxel by voxel method, which is guided by the quality of the connection between voxels. And that's very fast, but it's prone to errors in noisy regions. So we've developed a method which is kind of related most closely to Best Path, which the developer called Romeo, because it was implemented in the Julia language. And this is fast and accurate. And it's also a single step for multi-echo and multi-time point data. So basically, you only have to unwrap either one echo or one time point. So I thought I'd have a little look at how this works. So if we zoom in here on a few voxels here and pick them out, then you can see just by eye that all of these paler gray voxels belong to one kind of region. And here we've had a wrap, for instance, between these voxels. And this one here is meant to symbolize a noisy voxel with an unreliable phase value. So basically what you do in phase unwrapping in a voxel by voxel method is to compare the values, the phase values between voxels, and say that if the difference between those voxels in the phase is more than pi, then you add or subtract pi to it in order to reduce the difference to less than pi. And this process then really just becomes about making sure that you follow a path that goes through the object and doesn't go into noise. Because if we get an unreliable value here, then that would propagate and come back into the image. So it's all about really defining which voxels have got good signal and good connection between the voxels. So we have to define some kind of quality indices. And these are typically defined on a range between 0 and 1. So these values here between these voxels, they represent the quality of the connections between voxels. And so, for instance, this is 0.8. This is the best quality of connections between voxels that we're looking at. So you would do this unwrapping first on between these two voxels, then these two, and 3, 4, and go back here and do this direction. So basically, this spreads out this algorithm and tries to avoid the noise. So I think really the major plus points of Romeo are that these quality connections are well defined, and they reflect reliable phase and values. And the other one is the bookkeeping is done quite cleverly by the developers. So we actually use three what we call weights. We use a spatial phase coherence weights, which measures the quality reflects the quality of the connection between phase values. If we've got more than one time point, then we can use this temporal coherence. And if we've got the magnitude as well, we can use the magnitude coherence. Each of those is scaled between 0 and 1. And I'll show you what they look like. So if we've got, say, the magnitude at 2 echo times, the phase at 2 echo times, then these are what these three weights look like: the spatial phase coherence, temporal phase coherence, the magnitude phase coherence. We multiply them all together in order to get this quality map, which then guides the unwrapping through the objects. So we've tested this obviously on high resolution gradient echo data, but we'll show the results here for EPI data because that's what will turn out to be crucial for us. And you can see that it's not only a lot faster than Prelude, a bit faster than Best Path, but also the variation over time is a lot lower, which is kind of a good measure for the quality of the unwrapping. So we've got a lot smaller standard deviations there. And it's also got another couple of nice features. It's very easy to use. It's open source. So if you, for instance, just add this, then you get generated field map. If your phase and magnitude data is multi-channel, this could then be X, Y, Z, echo or time point, and then channel 5D data. Then this will also do a plural combination using the methods that I showed earlier. So because this is all offered open source, and we've had a lot of feedback from the community on this, this was picked as an editor's pick and reproducibility highlights, and you can see the developers there. There's Corbin Eckstein, who's a kind of wandering Julia and ICE developer, and Barbara Dumerska, who's now at UCL, both former PhD students as well. And it's all available on GitHub. And it's also found its way into some QSM programs like QSM-XT and Sepia. Okay, so moving from the phase to the magnitude now, one of the shortcomings of the magnitude in SWI is that we have these big areas of signal dropout, single echo gradient echo acquisitions, and that's really because of the long echo time that we're obliged to use while we're waiting for the phase to evolve. So we can remove that by using a multi-echo acquisition and then combining those echoes, weighting them so that that weighting tends to remove this area of signal loss. And this is our kind of background image in the SWI. The one problem with that is that we've still got this inhomogeneity that reflects the proximity of the brain to the coils. So that can be, for instance, a lot higher in occipital areas than at the front, depending on how big the brain is. So we developed a kind of quite simple heuristic method for doing that, or at least Corbinian did, Eckstein did, and by dividing this brain into boxes, and then doing a simple segmentation based on the median value, and then interpolating and smoothing between those values which are identified as belonging roughly to the same tissue class to give us an estimate of the blindness field. And if you smooth that and subtract it from your original data, it turns out to do a really nice job of generating a homogeneous magnitude image. And that's not just the case for a gradient echo. We've also used this for MP-range and flare based on a space sequence, and that gives a really nice homogeneity collection. Okay, so we've seen that we've got these phase wraps here, or residual phase wraps that come from homodyne filtering, and that we get rid of those if we unwrap and filter. That's based on work that was done by others a long time ago. So some of the stages in this processing of this improved multi-echo SWI, we've taken just the best results in the literature, and this is a good example of that. And then we combine these phase filtered echoes just for the SWI, like this over the echoes. And then we're having a look at this phase filtering function. So this is the phase mask function. It's usually used in SWI, which is called a positive filter. So basically, all negative phase values are set to 1, so they have no effect when you multiply them by the magnitude. And the positive values are scaled from 1 for a phase of 0 down to 0 for the maximum phase in the data. And that's usually multiplied by the magnitude a number of times, which is equivalent to raising it to a certain power. So for instance, for multiplication by 5 times, it's equivalent to raising this function to a power of 5. And we can see that this then introduces quite a lot of noise in these values. These abrupt values close to 0. So we adopted this sigmoid curve from the literature, which gives us a lot more natural values to the phase. Okay, so we've pieced all of those steps together, and we end up with this considerable improvement in SWI at 7T compared to the vendor single echo version. It's also got the advantage that because it's multi-echo, we can generate R2 star maps for it, which we do, and M0 images, and all of this runs on the image reconstructor. So we bundle this now with Aspire to run on the same platforms. So I don't know how many people are using this now, but it's available to everyone who has adopted our Aspire C2P. Okay, so that's an example from a healthy subject, 7T. This is a healthy subject, 11.7T from Neurospin. So I'm indebted to them for sharing this data with me quite recently. This data was first presented by Emmanuel Macron in this tweet in April, I think, which had 500,000 views. This is the same data, and I think I got the same slice in the data set, but looking at the SWI rather than just the magnitude. And I think you can see there's some improvement in the visibility of these vessels there spanning the cortex. Yeah, so trying to get one up on the clock. Okay, this is an example in a patient with multiple sclerosis who's got these paramagnetic rim lesions with penetrating veins. And you can see that compared to the product, the vendor SWI, we've improved the visibility of the lesion, both in the magnitude, and you can see that we've got some more contrast there after the magnitude. And we've also got a higher resolution and less blurring for use of multiple echoes in the processing I've been talking about. In this subject, we're also able to visualize a few very small paramagnetic rim lesions which weren't visible in the product SWI, though I have to say, 2 different scans, so it's possible that the subject moved very slightly in the acquisition of the product SWI, and I think that may well be the case. Anyway, you can see that we've got a very homogeneous image here with the visibility of some pretty tiny paramagnetic rim lesions. Moving on to some tumor imaging cases now, you can see that we've got erroneous bogus phase wrap here. It doesn't reflect any pathology, and we've got this popcorn appearance of susceptibility around this tumor here, which we don't have in the SWI. And these bogus phase wraps then accumulate in the minimum intensity projection. We don't have those with the processing that we're proposing. And so that's really just goes to show that these phase wraps don't just occur in the classic difficult ventral regions, they can also occur close to pathologies. Those pathologies then generate quite high magnetic field gradients around them. And we've also got T2 star, the initial signal 0. And this is another patient with a diffuse astrocytoma, where we can see that this pathology here is quite obscured by the presence of these phase wraps that we don't have here. And again, we've got the T2 star and then 0 to look at as well. Okay, so that was all some patient examples. Obviously, A big problem in doing SWI with these very high resolution protocols in patients is the long scan duration, talking about scan times from 6 minutes up to 9 or 10 minutes, with a resolution that might be, say, 0.3 millimeters in plane. And that is then a time scale on which we end up with motion artifacts in a lot of patients. So there's quite widespread interest in the community in using faster acquisitions. And I was lucky enough to be at the University of Queensland working with Marcus Bart's group when he was collaborating with Siemens in the development of a 3D EPI. And so this is work by Siemens developers, Jin, Kian O'Brien, and others, taking bits of code and help from international developers from Bonn and NIH. I'm working also with researchers from UQ, Monique Terrell, and others who've developed this very sophisticated 3D EPI with very flexible acceleration schemes with lots of different CAIPI shifts and reorder shifts and sampling schemes. And you can see that with that, it's then possible to reduce the acquisition time from 9.2 minutes for this QSM to just 58 seconds to the one on the right here, with still a very usable susceptibility map. And I was would then take this 3D EPI sequence to the Medical University of Graz and apply it at 3T. And here you can see that in this gradient echo acquisition at 5 minutes, we can see basically all of the same lesions in the 3D EPI data, and the susceptibility values in all of these deep gray matter nuclei are also quite comparable. Now, I'm pleased to say that some of our clear SWI developments as well flowed into this. Oh yeah, I should say that this was just found out this week, that this was an editor's pick for September. And it's also, some of this work has flown into a new work in progress package by Siemens here for XA, which is for susceptibility-weighted imaging at QSM using 3D EPI, but also Vibe and Wave. Lots of innovations there. Okay, so that was all the static susceptibility imaging, mostly SWI, but also the methods and the processing that's needed for QSM. I'm going to move now to fMRI and see how those methods that we've developed for SWI and QSM can be used to give us additional information out of the phase in fMRI. Of course, it's not entirely novel to use the phase in fMRI. It's not generally processed and stored, but there's been interest for over 20, 30 years in doing that, in sort of either in complex valued fMRI analysis or to identify large vessels based on the phase, work by Ravi Menon, and then also generating QSM, functional QSM from the phase itself. I'm going to see how these methods that we developed here can be used to yield extra information here from the phase. So the scheme looks something like this. Instead of just having our magnitude data and our fMRI analysis, we're also going to save the phase data, and I've written times 32 here as a reminder that we've got all the separate foil data which needs processing. And in the early slides in this talk, then I showed how it was possible to calculate the phase offsets, which we need to know in order to be able to do a proper phase combination over these channels. If we've got a multi-echo acquisition, here we don't necessarily want to do multi-echo EPI, but we can acquire multi-echo reference scan data, something like a pre-scan prior to the fMRI, from which we're going to calculate the phase offsets, which we can then use to phase correct all of these phase data here to generate combined phase data, which we can then unwrap using the methods we looked at. And then we're going to use these unwrapped phase data. We're going to convert them to field maps and use them both for a dynamic distortion and physiological noise correction of the fMRI data. And we're also going to look at how we can do a super resolution processing of these field maps in order to generate the QSM. So those are the three short subtopics of the second half of this talk: physiological noise correction, dynamic distortion correction, and super resolution QSM from fMRI data. So let's start with physiological noise correction. And our motivation here was to try and escape from the need to acquire data with physiological monitoring devices, respiratory belts, photoplethysmographs, and stuff, which may or may not be available at ultra high field, and which are generally a little bit tricky to can both be quite fragile in the measurements, quite a little bit unreliable. They always need timing with the EPI sequence, which may or may not be well integrated with the sequence. So what we want to do here is to try and get as much physiological information as possible from the magnitude and phase data. And the reason we think that phase might be useful in this context is that we know that the phase or the field in the head is changed by respiration. So what we do, we try and examine both the magnitude and the phase data to look for these physiological changes. And in the magnitude, we basically just mask the magnitude. The phase, we do the coil combination, phase unwrapping, and masking. And then if we just calculated the average values in the image in each image, we would have magnitude and phase time series sampled at the volume TR. And you'll often hear that it's not possible to detect, for instance, cardiac changes in fMRI data because we only sample at the volume TR, which is typically 1 to 3 seconds, and really the NICOS theorem tells us that we need to sample at twice the respiratory frequency, sorry, the cardiac frequency, with a resting heart rate of between 1 and 2 hertz. We're going to have to sample at 2 to 4 hertz or down to 250 milliseconds, which is below the typical TRs that we're using. Of course, we're not really sampling the signal at the volume TR. We're acquiring signal in each slice separately. So if we can remove slice-dependent effects, then maybe we can also then extract cardiac information from these. So what we do is actually reorder these time courses that we've got for all the different slices. And if you put those together without any correction for slice effects, then you can see respiration here nicely, these slow changes here. But we can see the effect of slice groups here. So this is one whole image where the amount of signal here that we're getting just depends on the position in the object. So we can get rid of this by just removing slice means and detrending each slice separately with a second order polynomial. And if we do that, we can see remove these slice position dependent effects, and we end up seeing something of the cardiac fluctuations here on top of the respiratory fluctuations. So the next step in the processing is to define bandpass filters, both for respiration and cardiac action. And that gives us then 4 time courses. That's cardiac and respiratory time courses, both in the magnitude and the phase. And then we see which of those, magnitude or phase, better explains the variance in the data. And we select that to generate regressors, which we then put in the GLM and see how much of those effects we can regress out. So we've compared that with our method, which we call prepare, where in a case where we do have respiratory belt and photoplethysmograph signal available, and we can see that we've got very high correlation between our prepare regressors and the regressors that come from the belt and photoplethysmograph, sorry, just from the belt signal at the moment for respiration. And in all cases, that respiratory information came from the phase. By all cases, I mean all subjects, and for these 4 different protocols that we acquired the data for. And you can see also that the correlation between these regressors that we've got and the belt signal is better than from that with another data-driven approach based on ICA that you might be familiar with Pestica. In the case of cardiac fluctuations, we've got the best results, possibly not surprisingly, for the shorter TRs. We've also got reasonable agreement with the photoplethysmograph signal here, but maybe some of the discrepancies possibly due to constant time shifts between the appearance of the cardiac signal in the MR data and the photoplethysmograph signal. And it's in any case better than with another approach that we tested it against. And in the case of cardiac signal, 50% of these regressors came from the magnitude information and 50% from the phase, which is maybe not surprising. So all in all, we see that an increase in the TSNR in the regions in which we assessed it, which was with our method here, which was equivalent to that with retro-IPOR based on the physiological monitoring unit information, and better, particularly in inferior brain regions in the brainstem in the test. So this is a method that we also put on GitHub, publicly available. So that's physiological noise correction. I want to look now at distortion in fMRI at 7T. So we know that SNR and bulk sensitivity are higher at 7T, but these strong magnetic susceptibility differences we've been looking at tissue interfaces with large local magnetic field inhomogeneities, and those lead to signal distortion, which I'm sure you're all familiar with, and that can really be quite large at 7T. So for instance, if you look here, it can be, depending on acquisition parameters, something between ½ centimeter and 1 centimeter, which can obviously be crucial in some contexts, like for instance, clinical fMRI. So the classic way to deal with this problem is to acquire reference scan data and look at the phase at 2 echo times and calculate a field map. And this goes back now 30 years to Jevin Balaban's seminal paper on field mapping. The problem with that, and that field map, then you would apply to all of the EPI magnitudes, usually in multiple fMRI runs, possibly over the course of up to how long an fMRI experiment takes, up to an hour. And the problem with that is then as we've seen, the field doesn't stay constant with time. We get these kind of drifts with drifts in changes in head position. We've got respiratory-related changes, and you can even see cardiac-related changes to the field here in this paper by Sarnes and Tal. So the aim of dynamic field methods is to map the field dynamically, usually using the phase of the fMRI data themselves. And this is originally done using multi-echo EPI, in this example by Elke-Visier, but where they had 3 echoes, but we don't always want to use multi-echo EPI. And in fact, it turns out we can use single echo EPI if we know these phase offsets. So how do we do this? Well, we do it in a similar way to how we did it for the high resolution gradient echo data. We have this equation for the phase evolution over time, and then rather than solving it for the magnetic field, we solve it for the phase offsets. So that's here. So we've got our reference scan data, which is again could just be a dual echo gradient echo scan, and then rather than solving for V0, we solve it for the phase offsets, and we subtract those from the time points here to generate a series of field maps from the phase of the fMRI data. So that's the method in principle. In practice, there are a few other effects we need to look at, and one is relates to these additional sources, contributions to the phase offset that I talked about right at the beginning. For instance, this pesky readout gradient. So if there's any mismatch between the switching of the readout gradients and the signal acquisition, that leads to a gradient in the phase, which is dependent on the polarity of the readout of that line. So it might look like this for odd echoes and like this for even echoes. So what we found in practice is that we needed 2 gradient echo scans with opposite readout polarity. And we've now then sped this up so we can get the same information from 1 triple echo scan, which is bipolar. That means we read the first and the third echoes out in one direction and the second echo out in the opposite direction. And if you look at it then in this method we're calling refill, reverse encoded image and low resolution pre-scan, which is a kind of refill sort of nod to top up. And then we see that this readout gradient in the gradient echo data can be calculated by combining these phase values from the 3 different echo times, which allows us then to calculate the phase offsets independent of these readout gradients. And also we can see that we can calculate these phase offsets without the need to unwrap the phase if we make the echo times equal to the echo spacings with the same trick that we used in Aspire. That means this is all pretty simple, so we can perform this processing on the imagery constructor. We can also massively reduce the resolution and increase the acceleration of this pre-scan, because we're only interested here not in the field itself, but in the phase offsets, which are quite low spatial resolution, low spatial frequency phenomena. We do, however, also need an additional scan here, like a single EPI volume before the fMRI run with the readout polarity reversed, because the readout phase gradient is not going to be the same for the EPI as for the gradient echo. This is starting to sound quite horrible, but I'll show you it's actually very simple from a user perspective, but I'll nonetheless drag you through the calculation of these dynamic field maps, if you'll excuse me. So the phase gradient here in the EPI is then just related to the difference between the phases of these 2 first volumes. So once we know that, we have everything that we need in order to calculate a reliable set of field maps from the phase of all of these fMRI time points. So we have that our time series of field maps is derived from the phase offsets, which we get from this reference scan. And then we have this phase gradient from EPI, which we get from this initial readout reversed volume. And then the only other factors left here are the phase of each time point, the magnitude of each time point, and then this integer here, which we get from unwrapping the phase data. So how does this look in practice, or how does it perform? Well, if we first of all compare it to a gradient echo field map, just say the first time points of this time series of field maps, we can see that in the absence of any deliberate motion or shim change there, we've got quite good agreements within a few hertz in the whole brain, where we know that there will be some respiration-related changes anyway. This actually agrees better than the top-up result, remembering the top-up is also only a static correction method, but we can see these kind of structures in the top-up field map which don't look quite right. If we calculate the difference between the refill field map, that's our dynamic field map, the gradient echo field map, and the same for top-up, we can see there's quite a lot of structure here which doesn't really look right. And if we apply both the top-up and the refill field map to correct the distortion in the volume, we can see that we're getting this kind of shadowing here in the top-up result, which isn't reflected in the original. And if we generate a distortion field based on the gradient echo field map, we can see that that is well corrected by refill, but that we've got some residual problems here in the top-up field correction, as well as top-up being a static method. So let's see it. Then also, if we deliberately change the field by changing the shim, then obviously the static field map correction doesn't work very well. We can see that the refill map does. So that's not only a sanity check, it also confirms that these phase offsets then are quite robust to changes in shim, but also we tested them for changes, quite large changes in head position. Okay, and then if we look at this in action, or see how this looks with a time series. So we've got our magnitude time series at the top. I should say that in this experiment, the subject is not moving their head, but they're moving their hands to and from their head like this to generate changes in the magnetic field without necessarily any motion. And maybe we could focus here on these kind of internal distortions, which we really don't want in this kind of task. It's quite an artificial kind of task, but we do see this kind of thing in patients, for instance, doing foot tapping or finger tapping. Okay, so that's the phase. This obviously needs processing. So let's move on to, once we've unwrapped that and scaled it and done these corrections, we've got the unwrapped phase here. And then we also want to introduce some kind of regularization. So you can see the time series of field maps here, and their fluctuation in this task. And then we've also got, I'm going to show you a comparison with the static field map correction here. So we've got the original data, and then we've got the static correction here. And you can see the brain shape has been nicely restored, but there are still large fluctuations within the brain. And then finally, if we move to go back a little bit as well, and then you can see that in this dynamically distortion corrected method, we've really got rid of all of these fluctuations within the objects, and all of them got really, it's just a few edge voxels which come from maybe a not quite perfect interpolation of the field maps. So basically that seems to work very well, just looking at it optically, and also it does lead to not only to a better geometric result, but it also leads to a higher time series SNR than a static method in this kind of task. Okay, so that maybe all got quite involved with how we calculate these field maps, but basically from a user perspective, it just needs a 5-second reference scan that replaces a field map. It's actually a lot quicker than a field map. We need one additional volume, which takes 1 TR, and all of this processing of most of the elements takes place on the scanner console, and then we read in the results of the phase offsets and these phase gradients into the EPI, so we can flexibly apply that to EPI phases, even if we don't have the source code. So that's distortion and physiological noise correction with field maps. And the final thing I want to look at is super resolution processing of these field maps to see if we can extract a decent quantitative susceptibility map. Okay, so how do we go about combining the phase images from an fMRI time series to generate QSM? In fMRI, we've got voxel sizes which are typically maybe higher than this at ultra high field, but not fantastic resolutions. They're like 2 by 2 by 3 to 4, and hundreds of them. And in QSM, we ideally want a susceptibility map that's got a resolution of something like 1 millimeter isotropic. So originally we thought to try and do this using the natural changes in head positions and super resolution reconstruction. It turns out that in most of our compliant subjects, these changes in head positions are very small compared to the slice thickness, which we probably anticipated that. So we've then returned to the super resolution literature and seen that actually you can get a better result, usually by changing the acquisition orientation. So what we're doing here is replacing the dummy scans, which would conventionally be all in the same plane as the fMRI time series itself, with dummy scans in 3 orthogonal orientations, so in sagittal, coronal, and transverse. And that gives us obviously a lot of through plane information, which we can use to generate a higher resolution QSM. Okay, so the potential advantage of this over 3D EPI is that it's not only going to be even faster, and then obviously in the context of fMRI, potentially just replacing dummy scans, so being no additional time for imaging, why we've called this a native, but it's also potentially going to be a lot more motion robust because we're acquiring each slice in something like 100 milliseconds or less. So we're acquiring the data using 2D SMS, gradient echo API, with 3 times the slice thickness as the in-plane resolution. Oops, going the wrong way. And we're acquiring those in sagittal, coronal, axial orientation, doing a distortion correction in each of those orientations, and then doing a super resolution reconstruction, which is not actually a full-blown model-based super resolution reconstruction. It's just actually a non-linear co-registration and voxel averaging. So I've shown you the magnitude image here, but let's look at the phase data. And we have to really pick for QSM at what point we combine these phase images in all of this processing scheme. So actually, we unwrap the phase data and do a distortion correction, and then do this background field correction to get the local field in each of these orientations. And that's the point at which we then do, that's what we work with further, and do the co-registration in the mean, and then do the dipole inversion to generate QSM. And if we look at the QSMs, you can see that they're slightly blurred compared to the 3D GRE, but they're really only 3 TRs in duration, and even faster than the 3D EPI. But I think the real advantage here is that in the context of motion, and here we've got the subject to do quite large motions during the acquisition, the 3D GRE is completely motion corrupted, as is 3D EPI, and we expected to, we acquired multiple time points and expected to have to throw out time points for this method here, where the motion really occurred at the worst during the acquisition. In the end, we didn't have to throw out any time points, and you could do this QSM processing with order of time points, also those where we had motion during the acquisition. And if we look at the magnitude now, you can see it even more clearly. So this is the native T2 star magnitude from the same data, and this is in the context of motion, where we've got motion corruption after 3D GRE, 3D EPI, and basically nothing visible there in the native acquisition. So we're actually starting to think about using this for methods beyond QSM and T2 star imaging, and look at other sequences, as others have been doing, to try and develop completely near motion artifact-free data with multiple contrasts. Okay, so that's it really. I hope I've shown you how some of these methods that have been developed for this field of susceptibility-weighted imaging and QSM for the high-resolution static case can be applied productively to fMRI data to generate field maps, also from single echo EPI data, which you can use for physiological noise correction, for dynamic distortion correction, and also using super resolution reconstruction to generate QSMs. So I'd just like to end by thanking people in my own group at the Medical University of Vienna, and then hosts at the University of Queensland, Medical University of Graz, and then collaborators at Siemens Australia, and UCL, and thanks to the Neurospin group who just lent me their data recently. And thanks to you all.
Thank you so much, Simon. This is beautiful images, wonderful talk. Thank you so much. So well, now since I'm not host, I cannot turn on my video.
So I pass the hosting back to you.
But that's okay. But yeah, you can pass it back to me, but don't turn off your video. Once it turn off, you cannot turn it on, it looks like.
Okay, let's see if I can make you host.
I can do reclaim.
Okay.
And yeah, don't turn off your video.
Now I'll leave my video on. There we go.
All right. Okay. So now it's question time, I guess. So you can, for the audience, you can type in a Q&A or type in the chat. I prefer the Q&A so everybody can see it. So we already had a question when you were talking about your first method. So this is from the adjacent document. Is it beneficial to separately unwrap each TE phase from each coil channel prior to performing coil combination, do you worry about noise in the phase image near the wraps? Unwrapping each channel separately is more computationally expensive, but I've seen to give cleaner results.
Yeah, I mean, my tendency would be against that. I think where the the challenge, I suppose it depends how you're doing your phase unwrapping. There are a large number of methods, like region growing, like Prelude, or even the Laplacian unwrapping, which I've not really shown, which is what we use in SWI. But I think for this voxel by voxel path-based, but actually also for the other methods, I think it's only a disadvantage to have multiple noisy images. I think your chance of entering into noises and following complex paths back into your object is higher. Got the extra computational load. So I think where you can combine the phase images into single high resolution, high SNR combined phase images, that would always be the way I'd go. I know that there was a paper out by a group from Queensland, which did separate channel QSM. I think probably the tendency then is not in that direction anymore.
Hey, great. Thanks a lot. So I was actually looking at some of the images you showed, those QSM, SBAT images in the first half. I was impressed. It looks like with your correction method, you can start to see some regions like the olfactory region around the olfactory bulb. Is that right?
I'm afraid you might over-challenge my anatomical knowledge.
Okay.
Yeah, I mean, I think we certainly can see closer to the base of the brain. There's been interest by some groups who want to use this for neuronavigation operations close to the base of the brain. Yeah, I think that there are no real downsides as far as I can see. Some people find like a little the weighting of the magnitude is a bit different to in a conventional SWI.
Right.
But I think generally it extends the regions of the brain over which you can expect normal results in healthy subjects, and also close to pathologies in patients who pathologies create these quite complex local fields.
Right. Right. Yeah, it'll be extremely exciting. I think I myself have lots of interest looking at the olfactory region. For SBI, if we can get even close to that region, then we'll see lots of blood vessels that's not easily seen by other methods. That'd be really great.
Okay. Yeah, I mean, maybe there could also be some optimization done for that purpose. I mean, there are a number of different weightings. The magnitude images, for instance, we weight them generally to create the maximum SNR, which is probably what you'd want in that case. Or you can also weight them to generate more contrast, for instance, if you're interested in lesion white matter contrast. Those are the ones I showed for the patient with multiple sclerosis with a paramagnetic rim lesion. But I think probably in that case, you might also just want to use obviously a lot shorter echo times and try to get to the shortest echo times possible. Maybe generally a short echo train. But I'd be happy to contribute if we can in any way.
Yeah, yeah. So the correction method you showed, especially in the first half, you said it's shared in multiple sites. Do you have a version of Philips site?
No. I mean, and this is unfortunately, I wish we did, but this is unfortunately, this is not a kind of vendor independent implementation. It would be nice to have this all with something like PulseSec and Open Recon or something. I think we and lots of other people who've done this, implementations particularly in the reconstruction environment can be very difficult, and it's a very steep learning curve.
Right.
So I think we're all quite excited by this Open Recon for Siemens, which I think will allow then a lot more vendor independence, and also to implement a lot more complex methods. So we're starting to apply at our center, some deep learning methods which can then put out, for instance, like spectral fitting on the console, using learned results by piping the result, piping the data out to something equivalent to used equivalent to a gadgetron without getting too vendor specific. But I hope that this is all a step towards vendor independence. But all I can say is that actually some of those parts of the processing already work very well on Philips, with sensory constructions, and
right.
all of this, for instance, what I showed in Clear SWI, that's all publicly available in Julia, and also in compiled versions for all operating systems on GitHub. So it should be very easy to apply.
Great. Yeah, I mean, Shuli is here. We'll bug him later. So we got some questions from Q&A. So great presentation. Is there a specific tool available to perform such functional MRI, functional QSM analysis?
Yeah, I mean, I sort of hinted at functional QSM and put that in an introductory slide, and I said by others because I'll be honest, I thought that with having some of these phase processing methods, I would be in a good position to do functional QSM. I've actually not managed to get anything usable or that I find very robust and solid out of it. So it's not been a very productive outing for me. I think there are some theoretical considerations about whether you'd expect to see phase changes in boxes where they might cancel around some of the sources that we have in the parenchyma, maybe possibly more with isotropic voxels. I don't know. Basically, I won't waffle around it too much. I just can't see anything in FQSM, in functional QSM. Nothing that I find that, I think that it's quite telling that a lot of the papers that are moving that direction, trying to do that, are looking at alternative sources of phase first, and how many of those need to be corrected and removed, from physiological noise to lots of other ones. Some great work by Gisela Hagberg and others on confounds in that kind of context. And I know that there have been some reports of FQSM changes, especially recently in LSMRM. There are groups working on it. I can't say that I've made any headway myself.
Yeah, well, that's my feeling too. I think at some point it'll be extremely useful if you have some sort of tools, if you want to push this method, for more general functional, MRI community to use. It'd be extremely useful for that. Okay, so next question from Alma for Goldman. Many functional MRI studies focus on cortex. Phase-based methods seem to always have some sort of tight brain mask. Is this a hard limitation for phase-based method for cortex researcher, masking pieces of cortex, for example, in the context of QSF functional MRI, or can we get rid of the tight brain masking?
That's a great question, and that relates really to steps in QSM, which I didn't put a lot of focus on here, really, for the background field correction. Then if in order to separate the internal and external fields, you need a mask, and that mask has to be reliable. And we've done some work on generating that mask, because we put one out as we derive one from the quality mask that we use for phase unwrapping. So we've got all these measures of the quality of voxel connections. And that is actually flown into some masking algorithms in Sepia and QSMXT and things like that. But to answer the question more directly, I think that to completely remove that masking requirement, we probably need to use something like a total field inversion method, maybe sort of deep learning, and get away from these tight masks that you need for QSM. If you're talking about phase itself, then there are also some problems with SWI and phase imaging on the surface of the brain. We've tried to create maps of the cortical veins using some quite early SWI, where the vessels then just don't have the shape that are expected by the vessel extraction algorithms like Frangi, for instance. They tend to be kind of open V's rather than nice cylinders. Those are probably it's probably work better now with the methods we've got. But when we looked at that as providing a means for additional means of localization for neurosurgeons, together with Alex Rauscher from Vancouver from UBC, then we really had a lot of difficulty segmenting those vessels on the surface. So I think it's probably better with these methods. Again, you probably need to go to shorter echo times, and then for QSM, probably away from background field correction.
Yeah, great, thanks. Actually, seeing almost question. This just reminds me. I mean, I was also wonder, do you see, so what kind of would that be? Well, how do you ask this question? So, do you see any advantage of from these phase-based method to do those so-called laminar functional MRI in certain regions?
Yeah, well, I suppose that relates then to the status of functional QSM, and I think that although there's been quite a lot of work on that, I think we're still at early stage. We're seeing some abstracts out, a couple of papers out. I cited one there by David Baller and the Nottingham group from quite a while back. But I think the results, there were a couple of results at the some REM which looked more promising. But actually, I thought the functional conductivity results maybe look probably more clear cut, and I couldn't see that there have been many attempts over the years to try and do even exclusion of large vessels from fMRI using the studies, and even those aren't that easy because of the huge disparity of scales between the fMRI and the SWI at the time. Maybe as those get closer together and we start using 3D EPI for both, that's going to be more possible. Yeah, I would say I haven't seen it yet.
Yeah. Indeed, this is related to your next question from Shu Li. Wonderful talk. Thanks, Simon. For the functional MRI study, since you have phase for each volume TR, what do you think about the values of doing functional QSM from those dynamic phase and the QSM data in terms of imaging neural activity?
Yeah, same answer again. I don't know what to add to that. I tried it, didn't work for me. As we've seen, the phase contains lots of sources of information, from drift to cardiac and respiratory-related fluctuations. Those have to be excluded. And then on top of that, I think that from the start, there have been both positive and negative susceptibility changes registered, which I think are not very easy to interpret. I know that there are groups working on that. I think that the Martino Center, some very good people who I'm trying to provide, or I am working with on providing some methods to, but they're really the experts in the interpretation of the laminar bold signal changes that you'll see from that.
Right. Yeah. Well, I can only say I'm very interested in this. I think there's lots of potential. So maybe we can check later more about that. So okay, I guess we went over a little bit, but I saw this is a really wonderful talk and a wonderful discussion as well. For people, I saw people start to leave after 12 o'clock here, but for people who stayed till now, thank you so much for supporting us. Once again, Simon, thank you so much for your time and for the talk and everything. I hope to see you sometime at some other conference soon.
Thanks very much.
Yeah, thank you so much. And for the audience, thank you so much again. We'll see you next month. Thank you. Bye. Have a nice day, everybody. Hey.